So now we're going to get into our discussion of the derivative and what a derivative is. So in calculus, there was always two big problems. There was the tangent line problem and then the area problem. The derivative deals with the tangent line problem, and then integration deals with the area problem. So to introduce the derivative, let's go and consider a physical phenomenon. Let's go and consider a car traveling down the road. And we're going to say that at t is equal to t1, we are at a position along the x-axis, x is equal to x1. So then the car starts to move a little bit, and at another time, t is equal to t2, we're now at a different position. Makes sense? Because when a car travels, it moves with respect to time. So now I want to consider velocity. So the velocity is pretty much just how fast the car is moving with a given direction. So now I have graphed out here what is called a position time graph. So this is a position time graph. So basically what this tells us is we're plotting position as time increases. So if you think of this point right here as the distance from the car at any point to the wall. So right here at t is equal to 0, well, the distance to the wall is going to be 0. So we're representing this horizontal distance as this vertical distance. So as t goes on, x is going to increase, which represents this car moving away from the wall. So that is the position time graph. Now let's go and consider what velocity is. So we have always known that velocity is going to be equal to a change in x over a change in t. So that makes sense because it's just how far you move in a given amount of time. So in this case, velocity can also be called the average rate of change. So in this case, this point right here corresponds to this point, t1, and it has moved x1 away from the wall. And so we say that this is x evaluated at t1. And same thing for t2, x evaluated at t2, because this is a function x of t. So it takes in a time as the variable and it outputs a height, or in this case, a horizontal displacement. So the important thing to note here is we can calculate this average rate of change. Normally we've done it where it gives you how much it moved in how much time. So graphically what that means is this slope. So this line almost doesn't look like a line here, but this line, the slope of this line is going to be rise over run. So this is your run, and this is your rise. Between the 2 points that we're interested in, so the velocity between these two times. So the rise, in this case, is going to be equal to x2 minus x1. Because that's just this height minus this height will give you the change in the height. So then the change in the time is going to be t2 minus t1. Now, this as well should look pretty familiar to basic 6th grade physics, because this is how we calculate the velocity. So the first big takeaway from this is that when we're given a position time graph, the slope of that graph will tell us velocity. And that's where we're about to get into the concept of the derivative. And the derivative of a position time graph is the velocity graph. So what do I mean by that? Well, if I wanted to know instead of what is the velocity from this point to this point, because that's easy. What if I wanted to know what is the velocity of this car at a certain time? So at a certain time t3 now, I'm not giving you two different times to where we can just use this formula. I want to know what is the velocity at a specific time. So if you can imagine taking a picture of a car going by you, the velocity or the average rate of change is just how far it moves in how much time. But if you took a picture of a car and just saw that car, the car could either be moving or it could be stationary. We don't know the difference because it is a snapshot in time. Well, here the important concept to note is if this car is not moving, then the velocity is 0. But if it is moving with a certain velocity v, and we take a picture of that, so let's say this is our picture. So we took a picture of this car. Well, what is this velocity in that moment? Now that doesn't make a lot of sense at first, and it didn't for me because I'm like, well, we don't have a change in x, nor do we have a change in time because we're given that it's just at this time. So this is a concept called instantaneous velocity. And the more you think about it, it should make more sense that even though it doesn't look like it's moving in the picture, it can't have a velocity of 0. Because we're saying, as this car is moving, and we take a picture right in the middle, t3, if we say the velocity is 0, then how could it be moving at all in between this time interval? So this car is moving at t is equal to t3 at a specific time. We want to know what is the velocity of this car at that specific time. And this right here, this idea, is called instantaneous velocity. So the velocity that we've always dealt with is an average velocity over 2 points. In calculus, we go into the idea that something can be changing the velocity in the moment. So instantaneous rate of change. So going back to the graph then, let's go and see if we can understand what that means. So if this right here are the two times and the slope is the velocity, the average velocity between the two times, then it should make sense that if I drew another identical copy of this graph, it should make sense that if we want, say, the instantaneous velocity, the instantaneous rate of change at the point t1, well, I already told you that the slope of a position time graph will tell us something about the velocity. This time, we're not taking the slope of this. This is a slope between 2 points. We're going to take one slope. And this one slope is called the tangent line. And that's where the tangent line problem comes in. We want to know this slope. So this is called a tangent line because it only hits the graph at one point. So now we have a line that only hits it at one point, and this line has obviously a slope. And so it's this slope, because we can calculate the slope. This slope is another xy situation, rise over run. We can calculate this slope tangential to the graph. And that is the graphical representation of what instantaneous velocity is. We're not going to go into how to do it yet, but this is the basic concept of the derivative. Because this right here is the derivative. A derivative is basically the instantaneous rate of change of something. And in this case, it's the instantaneous rate of change or the slope of the function at one point, whereas in algebra, we've always dealt with an instantaneous or a average rate of change over 2 points, which is, mathematically easier to calculate than a derivative. But this is the idea of the derivative, and we're going to see how do we calculate a slope that doesn't have a change in x like this. I drew this to show you that it has a slope. The line does have a slope, but we don't know what it is at that point yet because the change in x and the change in y is so small. But we're going to see that in the next video.